In this video, we're covering one-way analysis of variance, or ANOVA. So in this, we're going to be testing 3 or more populations that have means that are all equal. So our null hypothesis will always be mu1 is equal to mu2 is equal to mu3, or however means we're dealing with. We are strictly dealing with technology as always. This is the important vocab in terms. So starting with an F distribution, this is the shape of the distribution that we're going to be looking at here. And so just for your reference, we'll be talking about an F test statistic. So ANOVA is a method of testing the equality of 3 or more population means by analyzing the sample variance. And we're going to do all of it in our calculator. We're going to assume that the requirements are met. And so the procedure for testing this null hypothesis, we're going to use technology. We're going to identify the p-value, and then we're going to form a conclusion based on the following conditions. And when we reject the null hypothesis of equality, what this means, and this is super important, is that at least one of the population means is different from the others. We can't say that they're all different or anything else, just that one, at least one is different. So this is what we'll be doing, and we'll start always by entering our data into lists. Then we'll be doing the ANOVA test, and here we will have to use the comma key, so just keep that in mind. Now, for example 1, this is a ton of data, so I'm going to suggest that you just watch me do this one. I already have the data preloaded in, and then for example 2 and 3, you'll do it along with me. So for example 1, we're going to use the performance IQ scores listed and a significance level of alpha equals 0.05 to test the claim that the 3 samples come from population with means that are all equal. So our null hypothesis here is that we've got 3 situations. So the first mean is equal to the second is equal to the third. And our alternative is at least one mean is different. We can't say, I mean, we could list it all out. Mu1 is not equal to mu2, or, right, but this one's a little bit easier. So I'm going to enter this data into my calculator, and it's like magic. I've already put it in here. It's in my L1, L2, and L3, and that was no easy feat there. So those are all in there. And so I'm going to go to Stat, Tests, ANOVA, and I'm going to do, they're in L1, comma, so it's above the 7, L2, comma, L3, and I get there's a ton of stuff here, but what we care about is in the very top. Our F test statistic is 4.07, but what we care about is our p-value. Our p-value is 0.0195, and maybe we round this to say it's 0.020. And so this compared to our alpha here, this is less than or equal to 0.05, so we reject the null hypothesis. And what that basically is saying that there's sufficient evidence to reject the claim that the means are equal, right? We can say at least one mean is different. And so to go one step further, we cannot conclude, right? We cannot conclude that any particular mean is different from the others. We can't say that this one is different than that one's, but we can informally note that the sample mean is higher than the means for the medium and high blood, and we could have figured that out by running one variable statistics on each of these. And we'll be doing that for some of the other examples here just to kind of see what's going on. So again, when we conclude that there is sufficient evidence to reject the claim of equal means, we cannot conclude that any particular mean is different from the others. We can only say that at least one is different. So why do we have to do this? We've learned sample testing for 2. Why can't we just do it 2 at a time? It would require a lot more testing. And so this is actually much quicker, much easier, and it reduces the risk of a type 1 error. So let's do example 2 and 3. I encourage you to pause the video right now and enter this data into your list. I'm going to enter them into my L4, L5, and L6, but you can enter them into your L1, L2, L3. And press play when you have your data entered. So in this example here, we are given the amounts of arsenic in samples of brown rice from 3 different states, and the amounts are in micrograms and all the same serving size. We're going to use a 0.05 significance level to test the claim that the 3 samples are from populations with the same mean. So that's the claim we're testing, that mu1 is equal to mu2, which is equal to mu3. And so our alternative is that at least one is different. At least one mean is different. So do the amounts appear to be different in the different states? So we've typed in our data. So let's run our statistics. And it's at the very bottom. So if you go up, and mine are in L4, L5. So wherever yours are, you'll type in that data. Don't forget your commas. And we're looking for our p-value here. So we should get 0.000. And so we get our p-value is 0.0000, which is definitely less than or equal to our significance. So we're going to reject the null hypothesis, which basically says that at least one mean is different. So there is sufficient evidence to reject the claim that the states have the same mean arsenic content. So given that the amounts, and I'm reading right here, given that the amounts of arsenic in the samples from Texas have the highest mean, can we conclude that brown rice from Texas poses the greatest health problem? No, we cannot. Not based on the ANOVA, this analysis. This just says that they're different. It doesn't say anything else. So it's really important not to fall for that trap. And here is it written out a little bit more. So go ahead and give this one a try. This one you're analyzing something that's already been given to you. Press play when you're ready to see the solution. There you go. So we compare the p-value to the significance level. And we'll do one more example together. And you'll do one more entering the data on alone. So go ahead and pause the video and press play when the data is entered into your list. So I've got the data in here. And so this is the departure delay times for flights from New York to LA. Negative values correspond to flights that departed early. We want to test the claim that the different flights have the same mean departure delay. So the same mean. And the alternative would be that at least one is different. At least one mean is different. So we've got our data into our table, or excuse me, into our list. We're going to go to Stat, Test, ANOVA, L4, L5, and again, wherever you stored your data. And we get a p-value of 0.123. So how does that p-value compare to this? It is greater than 0.05, so we do not reject the null. So if we do not reject the null, we are saying that there is sufficient evidence to not reject the claim that the different flights have the same mean delay. And if you'd like to see that written out, there you go. So give this one a try and press play when you're ready to see the solution. And that concludes section 12.1.